Good morning. My name is Manoj Kumar, Assistant Professor, Department of Computer Science and Engineering, Kumar Engineering College. Today, in this lecture, we will learn about the AVL tree in data structure. So, this is the content that I will discuss in this lecture. First of all, we will learn about the AVL tree introduction. What is AVL tree? What is the definition of AVL tree? And what is the balance factor in AVL tree? And after that, we will see different rotation in AVL tree. Why the different rotations are needed in AVL tree and what is the concept of each type of rotation. So we will also learn about that. And after that, insertion in AVL tree. When we insert a particular node inside the AVL tree, then what step we need to follow to insert the AVL tree, or what are different steps that we use to construct a AVL tree for the given sequence of key. In the last, we will see the AVL tree construction problems that are generally asked in the AKGEC examination and sometimes also asked in GATE examination. Okay, so first we will see the AVL tree introduction. What is AVL tree? AVL tree is actually a binary search tree. Basically, it is a height balance tree. In case of AVL tree, the height of left subtree and right subtree is basically considered. And if we subtract the height of left subtree and right subtree, then it should be at most -1. So AVL tree is a binary search tree in which the difference of height of left subtree and right subtree of any node must be less than or equal to 1. Okay, AVL tree is also known as the height balance tree. And in the last, we will calculate the balance factor of each node. Balance factor of each node is calculated by considering the left subtree height and the right subtree height, and we subtract it. If the value of that particular node, balance factor of that particular node is 0, 1 or -1, then we will see that that tree is an AVL tree. The example of AVL tree are shown in figure. Suppose this is a tree. So for a tree to be AVL tree, at first it must be the binary search tree. First condition is tree must be the binary search tree. In case of binary search tree, means the right side for a particular node, the right side node must have the greater key and the left side node must have the less key. And after that, once the tree is binary search tree, we will calculate the balance factor of each node. And if the value of balance factor of each node is either 0, 1 or -1, then we can say that tree is the AVL tree. So for a particular tree to be an AVL tree, it must be a binary search tree at first, and after that the balance factor of each node in that tree must have the value either 0, 1 or -1. Suppose this is the first tree. Here the root is B and C is the left node, right node of the B, and A is the left node of the B. So this is BST. And against the balance factor of each node A, there is no left children and right children of A. So balance factor of A is 0. In the same case, the balance factor of C is 0. Again, if we calculate the balance factor of B, then there is one node in the left and one node in the right. So 1 - 1 is 0. So balance factor of B is 0. So in this tree, the balance factor of each node is 0. So this is an AVL tree. Now let us see this particular tree. Here the root node is C. B is the left child of C and A is the left child of B. So in this case, the balance factor of A is 0 because there is no left child, no right child of A, and the balance factor of B is 1 because in left side there is one node and in right side of B there is no node. So left minus right will be 1. Again, for the C, when we calculate the balance factor of C, then in the left of C there are two nodes, 1, 2. Or again, if we calculate the height, then 1, 2. And in right, there is no node in the C. So the balance factor of C is 2. Now, in this case, since in this tree, the balance factor of C is 2, it means it doesn't have the value either 0, 1 or -1. So this tree is not an AVL tree. Okay, so for a tree to be an AVL tree, it is necessary that it must be a binary search tree first, and after that the balance factor of each node in that tree must be either 0, 1 or -1. In the same way, this is a different tree. Here the balance factor of A is -2. Basically this is -2, 0, this side is -1, and this is -2 because in case of there is no left child of B, so HL minus HR for B, that will be the -1. Okay, and in the same way for A, that will be -2. Okay, so the valence factor of A is -2. So this tree is also not the height valence tree, or this is also not an AVL tree. Next, different type of rotation in AVL tree. Why do we need the rotation? Actually, whenever we construct an AVL tree, or whenever we insert a, suppose a valence tree is given. Okay, an AVL tree is given to us. Now, if we want to insert a new node or new key in that AVL tree, so if the tree become unbalanced after insertion, in the same way, AVL tree is given, and when we delete a particular node from that AVL tree, so after deletion, the tree become unbalanced. So when we insert a new node in the existing AVL tree, or when we delete a particular node from an existing AVL tree, so if after insertion or deletion tree become unbalanced, so that to make that tree balanced, we need to perform some kind of rotation. So there are 4 type of rotation in AVL tree: left rotation, right rotation, left right rotation, and right left rotation. So when we insert a particular node in the existing AVL tree, or when we delete a particular node from the existing AVL tree, so after insertion or deletion, if tree become unbalanced, so to make that unbalanced tree balanced, we need to perform this kind of rotation, and we will discuss in this presentation one by one. So at first we will learn about the left rotation. What is left rotation? Why do we need it? And in case, in which situation we need to perform the left rotation? What is the concept of left rotation? Okay, suppose this tree is given. Okay, so here the node is A, and again this is the right, node B is in the right of node A, and node C is node A. Suppose this is node A. We insert a new node B here. So valence factor of A is 0, valence factor of B is 0, and valence factor of A is -1. Now, suppose we are inserting a new node C here. Okay, so now the valence factor of C is 0, valence factor of B is now -1, and valence factor of is -2. This is -2 and -1. So when we insert a node in the right subtree, in the right subtree of a particular node, again please try to understand, this is a particular node A, and B is in the right side of A, and C is in the right side of C. So here the valence factor of A is unbalanced, it is -2. Valence factor of A is -2. So valence factor of A become -2 when we insert a new node C in the right subtree of A. Right subtree of A consists what? V. And we insert the new node C in the right of. So when we insert in the right of a particular node, and tree become unbalanced, in that situation we need to perform the left rotation. So here we will rotate this tree to the left direction. This is the left direction to make it balanced. So when we will rotate it left, then this will be the final tree. Okay, after left rotation. So what happened here? Now calculate the valence factor. Valence factor of A is 0, valence factor of C is 0, and valence factor of B is 0. So this is the left rotation. So whenever we are inserting a new node in the right subtree, in the right subtree of a particular node, it means we are inserting the node C in the right subtree of A. Okay, so in this case we need to perform the left rotation. Next is the right rotation. Suppose this tree is given to us. Here the valence factor of A is 0, valence factor of B is 1, because there is no child in the right of the B, and valence factor of C is 2. So here this is left and left. So suppose this valence factor of C is 0. When we insert B, then valence factor of B is 0, and valence factor of D is 1. Now when we insert A, then A will be insert here according to the binary search concept. When we insert a new node in AVL tree, then we will follow the rule of the binary search tree. It means if the value is less than the current node, then it will insert it into the left subtree, and if the value of or key is the new node node to be inserted is greater than the current node, then it will be into the right subtree. Okay, since A is less than B, so it will insert it in the left. Now the valence factor of A is 0, valence factor of B is 1, and valence factor of C is 2, because there is no node in the right direction of the C. So this tree become unbalanced. So this tree become unbalanced when we insert a new node A in the left subtree, in the left subtree of C. This is C, left subtree of C consists B, and we insert node A in the left of B. So when a particular node is inserted in the left subtree of the current node and tree become unbalanced, then we need to perform the right rotation. So here what we do, we will rotate this tree towards the right direction. So when we will rotate it, then B become the parent and A will be the left child of B and C will be the right child of B. So here the balance factor of each node is 0. Now this is the balanced tree. Next, third is the left right rotation. Whenever we need to perform the left right rotation, consider this situation. Here a node is C and we insert B, A. Since A is less than C, so it will insert it in the left. Now we are going to insert B. Since B is less than C, sorry. See, B, we have to insert B. B is less than C, so it will insert it into the left subtree of C. Again, since B is greater than A, so B will be inserted in the right direction or in the right subtree of node A. So B will be inserted here. Now, as soon as we insert the B, then balance factor of this is 0, balance factor of this is 1, and balance factor of this is, this is minus 1. Balance factor of this is minus 1, and balance factor of C become 2, because there is no right child, okay, of C. So in this case, tree become unbalanced. So tree become unbalanced when we insert a new node in the right of left subtree. Left subtree of C is A, and in the right of A we insert the V. So when we insert a new node in the left of left subtree, in the right of left subtree of a particular node. Okay, so left subtree of C is A, and we insert this node in the right of A, and tree become unbalanced. In this case, we need to perform the left right rotation. Again, this left right rotation is a combination of two rotation. First, we will perform left rotation, and after that we will perform the right rotation. So first we will perform the left rotation in context to the node which is attached to the node which become unbalanced. C become unbalanced, so we will perform the rotation in context to A. So left rotation will perform in context to A. So A will go down and we will become the parent. So here now the balance factor of A is 0, B is 1, and C is 2. Now, when the left rotation is performed, after that we will perform the right rotation in context to V. So when we will perform the right rotation, then C become downward and we will become the parent. Okay, so this will become the situation. So so when we perform the LR rotation on this tree, then this will be the final tree. So this is the result of left rotation. Okay, and this is the result of right rotation. Okay, next is the left right rotation. Again, left right rotation is a combination of two rotation. First we perform the right rotation, and after that we perform the left rotation. It means in right left rotation, it is a combination of right rotation followed by the left rotation. When it will be performed, suppose we have a node A. Now we are going to insert C. Since C is greater than A, so it will insert in the right. Now we are going to insert B. B is greater than A, so it will insert in the right subtree of A, but V is less than C, so we will insert it in the left of C. So balance factor of B is 0 and balance factor of C is minus 1. Again, balance factor of A is minus 2. Okay, because there is no left child of A. So in this case, the balance factor of A is unbalanced. So we need to balance it. But when balance factor of A become unbalanced, when we insert a node B in the left of right subtree of A. C is the right subtree of A, and we insert new node B in the left of C. So when we insert a new node in the left subtree of right subtree of a particular node, then we need to perform the right left rotation. So at first we perform the right rotation. Okay, in right rotation, B will be the parent. So this is the result of right rotation. Okay, this will minus 1 and this will minus 2. Now this is again unbalanced. So to make it balanced, we need to perform the left rotation. So when we perform left rotation, then B become the parent and A and C will be the child of C. So in this case, balance factor of A is 0, balance factor of C is 0, balance factor of B is 0. So this is the balance tree. So the RL rotation, this is the given tree, this tree become unbalanced when we insert B. So when we perform the RL rotation on this tree, then this will be the result. So in AVL tree, when we insert or delete a particular node, and after insertion or deletion the tree become unbalanced, in that case, to make it balanced, we have to perform left right rotation and right left rotation according to the situation. Okay. So now we will see the steps of insertion and AVL tree. What are the algorithm to insert a particular node or to construct an AVL tree for a given sequence of keys? So in step 1, first we insert a new element or new node into the tree using the binary search tree insertion logic. What is the binary search tree insertion logic? I already told, if the value of the new node is less than the current node, then this new node will be inserted into the left subtree of current node. If the value of new node is greater than the value of current node or key of current node, then the new node will be inserted into the right subtree. So by following these rule, we will insert a new node in the AVL tree. Okay. In step 2, after inserting the new node, we will calculate the balance factor, or we will update the balance factor of each node in AVL tree. Step 3, when the balance factor of every node after insertion is 0, 1 or -1, then tree is balanced. We will simply proceed to insert the next node. There is no need to balance if the balance factor of each node is 0, 1 and -1. But in step 4, after inserting the new node, if the balance factor of each node is not 0, 1 or -1 of A, or any one node has the balance factor apart from it 0, 1 or -1, or any node has the balance factor like 2 or -2, then tree become unbalanced. Okay. So in order to after insertion, in order to make the tree balance, if it become unbalanced, we need to perform a suitable rotation. Okay. So let us discuss some problem based on the construction of AVL tree. Construct question 1. Construct AVL tree for the following sequence. This sequence of key is given to us. Now we have to construct the AVL tree. So the first key is always considered as the root of the tree. So 14. There is no left child, right child. Again, balance factor of 14 is 0. Next value is 8. Since 8 is less than 14, so it will go to left. Okay. Now balance factor of 8 is 0 and balance factor of 14 is 1. Now next node is 12. 12 is less than 14, so it will go in the left side of 14, but 12 is greater than 8, so it will insert it in the right direction of in the right subtree of 8. So now the balance factor of 12 is 0, balance factor of 8 is 1, and balance factor of 14 is 2. So now the balance factor of 14 is 2. So when this tree become unbalanced, now in this situation, what is the which rotation will be performed? This is the left or right. Okay, so LR rotation will be performed. In LR rotation, at first we perform the left rotation. So when we perform the left rotation, then 12 become the here the left rotation is performed. So 12 become the parent, or 8 become the child of 12. Now balance factor of 8, 0, 1 and 14. Now we need to perform again right rotation. So when we perform the right rotation, then 12 will be the parent, this will be the tree. Balance factor of 8, 0, 0 and 0. Now we insert the next value 46. 46 is greater than 12. Okay, so it will insert into left or right of 12. Again 46 is greater than 14, so it will insert it here. So after inserting 46, the balance factor of each node is balanced. It is 0 or 1. Now next we will insert the 23. Insert the 23. So when we insert the next value is what? 23. So when we insert the 23, then it will insert here in the left of the 46. So the balance factor of 23 is 0, balance factor of 46 is 1, and balance factor of 14 is -2, and balance factor of 12 is -2, and it's 0. So here in this case, what will happen? Two node has the unbalanced factor 14 and 12. So in this situation, we will adjust the balance factor of 14. So after adjusting the balance factor of 14, the balance factor of 12 will already adjust. So this is the left and this is the right and this is the left. So RL rotation will be performed. So in case of RL rotation in context to this particular tree. So when we perform the RL rotation, then what happen here? It is first we perform the right rotation followed by the left rotation. So first we perform right rotation. So when the right rotation is performed, then 46 become here and 23 will be the parent. So this will be the subtree, balance factor 0, balance factor -1, -2. Now again we perform the left rotation on this particular tree. So when we perform left rotation, then 23 become the parent and this will be the tree and balance factor of this. So this is the our tree. Okay, now we will insert the next value. Next value is 5. So when we insert the 5, then it will inserted here. So balance factor tree is balanced after inserting 5. Next we will insert 77. So when we insert 77, it will go there here and balance factor 0, -1, -1. And again this is 1 and this is -1, no need to balance. Next we insert 88. 88 will be inserted here, balance factor 0, -1, -2, -2 and -2. So here 3 node has the unbalanced factor, so we need to perform balance it, and this is the right and right. So here when we left rotation is performed, so when left rotation is performed, then 88 will left 77 here right left rotation is performed in context to 46. So 77 become the root and 46 become the left child and 88 become the right child of this. Balance factor is 0, 0, 0, 0, -1 and again balance factor of this is -1. So tree is balanced. Next we insert the 20. So when we insert the 20 will insert will be inserted here. Balance factor 0, 1, again 0, 0, 0 and balance factor is -1. So this is also balanced. Okay, so this will be the final tree for this particular given sequence. Let us see one more example. We have to construct the AVL tree for this sequence. So first node I will consider as the root. So balance factor of 1 is 0. Now we insert 2. So balance factor of A become -1. Okay, and balance factor of 2 is 0. Now we insert the 3. 3 will be inserted here, 0, -1 and balance factor of is -2. Okay, so become -2, so right and right. So in this situation we need to perform the left rotation and 2 become the parent. So this will be the AVL tree. When we insert 4 will be inserted here. So 0, -1 and again -1. Okay, tree is balanced. Next we insert 8 will be inserted here. So balance factor 0, this is -1, -2 and -2. So we need to perform in context to this. So this is the right. So we will perform the left rotation. So 4 become the parent and this will become the tree 0, 0, 0 and this is the -1. Tree is again balanced. Next we insert the 7 will be inserted here. So 0 or 1 and this is -1, 0, 0 and here right. Okay, so we need to perform the left rotation. So when we perform the left rotation, then 4 will become the parent and 2 will this will be the tree 0, 0, 0, 0 and 1, or again here the balance factor 0. This is the balance. Next we insert here 6. So when we insert 6 will be inserted here. Now the balance factor 0, 1 and 2. Okay, balance factor 1. This become unbalanced. So we will perform this is the left rep. We will perform the right rotation in context this particular tree. Then 7 become the parent or 6 become the right child. Again the balance factor 0, 0, 0, 0, 0, 0 and 0. So this tree is the balanced tree. Okay, now insert the 5. So when we insert 5, it will be inserted here in the left of the 6 and the balance factor is 0, 1, 0, again 1, 0, 0, 0 and balance factor 1, 2, 1, 2, 3. So balance factor is -1. So this tree is also balanced. Now insert the 11. 11 will be inserted here. Balance factor is 0, balance factor -1. This is 0, 1 and balance factor is 1 2 1 2 0. Balance factor is 0 0 0 and 1 2 1 2 3. So balance factor is -1. This is again the balance tree. Insert 10. So 10 will be inserted here. Balance factor is 0 1 and -2 0 1. Again here 1 2 1 2 3 -1. Again 0 0 0. Here 1 2 1 2 1 2 3 4. Okay, so in the left there is 2, in the right 1 2 3 4. So 2 minus 4, that is -2. So balance factor is -2. So we need to perform the balance of this. This is in the right RL rotation. So first we perform the right rotation. So when we perform right rotation, then 10 we come here. Okay, now we calculate the balance factor. So when we calculate balance factor 0 0 0. So this again after inserting the 12 will inserted here. In this situation, balance factor of 12 is 0. Balance factor is -1 0 -1 0 1 and again 1 2 1 2 3 -1 1 2 and 1 2 3 4 -2. Okay, so we will perform the rotation with context to this. So we will perform the left rotation. So when we perform, because in the right of right, so we will perform the left rotation. So left rotation perform, then 7 become the parent, and all this tree will be become the left subtree of this, and this will the right subtree of this. So balance factor 0 0 0 0 1 0 0 0 -1 -1 and 1 2 3. Left, in the left side there are 3, in the right side 1 2 3. So balance factor of 7 is 0. So this will become, this is the AVL tree. In the same way we will construct this AVL tree. Okay, this is the binary search tree and we have to insert the 7. So after inserting the 7, tree become balance. So in this way we can construct the AVL tree for a given sequence of node. Okay, thank you.